In this lesson we're going to look at the penetrating and ionisation power of radioactive emissions. Before we do that, let's just remind ourselves of the characteristics of the three types of radioactive emission that we've seen in the previous lessons. First of all, we've got the beta particle. We remind ourselves that that's an electron and it's got a charge of -1, and being an electron, it's an extremely small particle compared to the alpha particle, which is a helium nucleus. That means it's got 2 protons and 2 neutrons, and it has a charge of +2. But it is considerably bigger and heavier than the electron. We remember that the mass of an electron is approximately 2,000 times less than the mass of a proton or a neutron. So remembering that the helium nucleus, or the alpha particle, has 4 nucleons, 2 protons, 2 neutrons, that means that the mass of the alpha particle is approximately 8,000 times greater than that of the electron. Okay, so let's just make a note of that. So that's approximately 8,000 times the mass of the beta particle. And then finally we've got the gamma emission. Now that's not a particle at all, it's a type of electromagnetic radiation and belongs to the same family as light or X-rays or microwaves, for example. So this has no mass and has no charge. Now before we consider their penetrating powers, well, let's just remember their speeds as well. Beta particles tend to be fairly fast moving objects, whereas the alpha particles, because they're much heavier, tend to be slower moving. And the gamma radiation, which is a type of EM radiation, well, that's extremely fast moving. They move at the speed of light. Alright, so bearing these characteristics in mind now, we can now understand their various penetrating powers. So this is the classic sort of comparison setup, and we've got different types of material here. We have mica, flesh is often used as the second material, or cardboard, and here we've got a thin sheet of aluminium and a fairly thick plate of lead. So we're going to compare the penetrating powers of these three different types of radioactive emissions. First of all, we'll take the alpha particle. Well, the alpha particle will penetrate a thin sheet of mica, but it will not penetrate flesh or thick cardboard. Okay, this is understandable because it's a slower moving particle and it's a much bigger, heavier particle than the beta, for example. So it gets easily blocked by matter. It interacts with the matter easily and therefore gets blocked. Now the beta particles are much faster moving and they're much smaller, so there's much less interaction. That means that they can penetrate a lot further. So our beta particle will go through mica, it'll go through flesh, but it'll get blocked by our thin sheet of aluminium. And then finally our gamma radiation, that's not a particle, it's got no charge, it's got no mass, so there's a lot less interaction between the gamma particle and matter. That means that it can penetrate a lot further, so it will penetrate easily through our thin sheet of mica, it'll pass through flesh or cardboard, it'll pass through our thin sheet of aluminium, but it will eventually get blocked by our thick lead blocks. So lead is very good at absorbing all three types of radioactive emission. Just summarising again, because the alpha particle has a much bigger mass, it has a larger charge, it is slower moving, it will interact a lot more with matter and therefore it'll get blocked easier. Okay, the beta particle has a much lower mass, it has a lower charge on it, and it is a lot faster moving, so it is able to penetrate much further than the alpha particle. And the gamma radiation, which has no mass at all and no charge, and it moves at the speed of light, can penetrate a lot further, but it will eventually interact with something and get blocked. Now that's the penetrating capability of these radiations, which is actually directly related to their ability to ionize, but in the opposite way. So the alpha particle can't penetrate very far because it interacts very easily with matter, and when it interacts it causes ionization. What does that mean? So let's imagine that our huge alpha particle is passing through a gas, say argon for example, and as it does so it will collide with electrons and knock them out of their orbits and cause the particles to become ionized. So we get a collision here, bang, and this electron gets knocked out of the orbit and a particle becomes ionized. It acquires a positive charge because the negative electron has been knocked out of the orbit by the alpha particle. Okay, so alpha particles can quite easily cause ionization because they're quite large, they have a larger charge on them, and they're slower moving, so there's much more interaction between a gas, a liquid or a solid as it passes through. So we can say that our alpha particle is strongly ionizing. It will actually only be able to pass through a few centimeters of air before it ionizes some molecule or atom. Now our beta particle, which has a much lower mass and travels much faster and has a lower charge, will interact less with matter as it passes through, as we've just seen, and that means it ionizes less. Okay, so we say that the beta particles are moderately ionizing. There's less chance of it interacting with an atom and knocking an electron out. And finally, our gamma radiation, as we mentioned earlier, is able to penetrate much further than the other two because it interacts much less with matter. That is to say, it's much more weakly ionizing. Okay, so there's less chance of it interacting with an electron in an atom and knocking it out. However, it will happen eventually. Eventually it will hit something and it will cause ionization. Okay, so we say that the gamma radiation is weakly ionizing. So just to summarize, we can say that alpha particles are poorly penetrating but strongly ionizing. Beta particles are moderately penetrating and moderately ionizing. Gamma radiation is strongly penetrating, it will go a long way through matter, but weakly ionizing. Now we'll look at the medical consequences of this ionizing power and penetrating power in a later lesson when we look at the dangers of radioactive emission in the context of cancers, but also the medical uses of radioactive emissions in treating cancer.